And what we are doing today is almost identical to what we were doing yesterday, except we're changing some terminology and we're writing things or communicating things slightly differently. What we're going to be doing is writing an absolute value function as what's called a piecewise function. Recall that the absolute value of a negative quantity is the negative of the quantity. I should have read that through and think about that. As an illustration, the absolute value of negative 3 is 3, which is negative of negative 3. If I say, what is the absolute value of negative 10, since the thing we're taking the absolute value of is negative, to make it positive 10, we can take the original quantity and multiply it by negative 1. So what I'm telling you is the absolute value of something is the negative of that argument, of the negative of that thing, if that thing's negative. Because the negative of a negative makes it positive. You understand how confusing that sounds to somebody who just walked in the room and thought, well, I don't know, what's he even saying? Hopefully it makes sense to you. Okay, the absolute value of a negative quantity, and I'll even write it this way so you can see it. The absolute value of some negative thing will always be equal to negative 1 times that negative thing. There's another way to write it. I could say, or the absolute value of a thing, and this is maybe even better, is negative 1 times the thing if the thing is negative. In fact, I think that's what you should be saying. Right? So, we're going to use this idea to write absolute value functions as separate functions without absolute value signs. What we're going to be doing is taking a function like the absolute value of x, f of x rather. We're going to be taking a function like the absolute value of f of x and writing it as two different functions, neither one of which has an absolute value. Okay? And when we do that, this is called piecewise. You're taking a function and you're writing it in piecewise fashion. You're writing it in pieces. So for all of these examples today, and this is all we're doing today, we're writing the piecewise function and we're sketching the result, or we're sketching the original function. So here's how it works. Do you agree that if f of, you have to think carefully about this. Thank you. Absolutely. Sorry about that. Do you agree that if f of x is the absolute value of x, sometimes f of x is simply x? When is f of x just x? In other words, when don't we even have to look at the absolute value signs? Sukhman?
When the number is positive.
Or there's another one other than just positive.
0.
Or 0. So what we do is we say f of x is x if x is greater than or equal to 0. And I want you to think carefully about what I'm about to say. If f of x is the absolute value of x, f of x will just be x if we don't need the absolute value signs. When don't we need the absolute value signs? Well, when the thing inside the absolute value signs is greater than or equal to 0. What will the function be equal to if x is negative? Zach, do you think you know? Negative x. The function f of x will be equal to negative x if x is negative. Because if x is negative, negative x will be positive. Don't mess up your graph, but I'm just pointing out that this, in terms of x, is from and including 0 all the way to the right, correct? This is not including 0 and everywhere to the left. Yes? Okay. Hold off on drawing anything just yet. Do you know what y equals x looks like as a graph? Do you know what y equals x looks like? Yeah, it's a line through the origin at an angle of 45 degrees, correct? So y equals x, and don't draw this, is that line, right? But y equals x is only true if x is greater than or equal to 0. Which means we only draw it from here up, there we go, into quadrant 1. Because that function is only valid where I've highlighted the yellow part of the domain. Do you know what negative x looks like as a function? Well, it's a slope of negative 1 through the origin, so it's this line. But this graph is only valid for values of x less than 0, so it starts here. So in this region, in here, y is equal to negative x, where x is less than 0. In this region, y is equal to positive x, where x is greater than 0. These lines that I've put here are just me talking about where each piece exists. And now you can draw it if you like. Sukman.
Like when the function is y equals negative x, does the line not like go to 0?
No. No. So if I were to show you both parts of this, and I'm just using different colors to make my point. What Sukman is asking is, for the part of the graph that's on the left, where y is negative x, does it reach the origin? And the answer is no. What we have is this part and this part. So the part that I'm highlighting in yellow, both the domain and the definition of the function, the part where we simply strip off the absolute value signs and we don't worry about them, includes y equals 0. Because the absolute value of 0 is still 0, so we don't need the absolute value. The part that gets, well, and really, everybody, this is exactly what we were doing yesterday. We were taking something that was below and we were flipping it up, weren't we? The difference is now what we're doing is we're flipping it up and we're telling you what the equation of that flipped up part is. But in answer to your question, let me go back to where I belong here. That'll work. the answer to your question is that that part on the left does not include the origin. But luckily, the part on the right, so if you like, we can get rid of all of this. Get rid of that, get rid of that. So this is the part on the left, which does not include the origin. This is the part on the right, which does, so luckily that fills in that point. Okay. Let's try one more. Y equals the absolute value of 2x minus 4. So, I'm going to try to approach this now in a more general sense. There will be a piece of this function that is y equals 2x minus 4, and there will be a piece of this function that is negative 1 times 2x minus 4. The piece where y equals 2x minus 4 is the piece where the absolute value signs are not needed. And this is going to be where 2x minus 4 is greater than or equal to 0. Sukman, do you understand that your question is identical to asking where does the equal go? Does it go on this inequality or this inequality? And it always goes on the top one. Do you catch my drift? Okay. So if 2x minus 4 is greater than or equal to 0, you don't need the absolute value signs. This one is going to be where 2x minus 4 is less than 0. And again, I keep repeating this and I hope it sinks in. If 2x minus 4 is negative, and it's what's in the absolute value signs, then you have to take it and multiply it by negative 1 to make it positive. And that's what's happening here. But what we want to do is write what x is here. Not what 2x minus 4 is, but what x is. And when you solve this inequality, you can add 4 to both sides, and when you divide both sides by 2, you end up with x is greater than or equal to 2. And that means this will be x is less than 2. So, Sukman, this tipping point where x equals 2 is going to be always where y equals 0. Because that's where it changes from being negative to positive, or positive to negative. And that means that this point is going to be a point on this function. I want to get rid of that. That point is going to be a point on that function. And everywhere to the right of 2, that will be the function. Everywhere to the left of 2, the other thing will be the function. And all you need to graph this is to recognize that the slope of this line is 2. So we can start plotting a point. I'm plotting a point, and we can draw this. This line that I'm about to draw that I don't want you to, this line is y equals 2x minus 4. But we only plot it for where x is greater than or equal to 2. That means everywhere to the left of this point, this will be the function, which, by the way, is negative 2x plus 4. And that has a slope of negative 2, which means you go over 1 and down 2, which means this is what it looks like. I meant to use a different color here. I apologize. Everything to the left of 2 is that function. Everywhere to the right and at 2 is the other function. Let's try the next one in a slightly different way. And there's this topic, there's another topic in this unit, and then there's one topic later on in the course, in the last unit, that all go for students. Yeah, okay, yeah, I think that makes sense. And then you get to the point where you go, yeah, that makes sense. And then you start working on it on your own and you go, what am I doing? It's natural. This is a weird kind of way to look at things. So let's try this one differently. Let's try instead graphing the absolute value function first before we write the piecewise functions. Now this is something we learned how to do yesterday. If I look at this function, you should know what this looks like. It has a slope of 1/2 and a y-intercept of 1. Correct? Math 10. So you have an eraser. If you're doing this in pen, don't commit yourself to it yet. And I didn't give you rulers, but I think you can draw with a steady hand. That this is the y-intercept, and this graph has a slope of 1/2, which means you go over 2 and up 1, over 2 and up 1, over 2 and up 1, right? Going in the other direction, my question is this. Looking at those points, will this point stay the same when we take the absolute value? No, it'll move, right? Because it's below. Will this point? It'll move. Will this one move? No, that means when x is greater than or equal to -2, the function doesn't need the absolute value signs. This is another way to write out the piecewise function. That f of x will simply be equal to 1/2 x plus 1 if x is greater than or equal to -2. And that includes this point. For this part, we have to multiply the original function that we were absolute valuing by -1 to flip it up. And after all, that should make sense because a function is y, and you multiply y by -1. Capiche? So it would look like this. Well, let's sketch this with a graphing calculator. Quadratics are tougher. I think you should know what this looks like, because you should know what y equals x squared looks like, and this is shifted down 5. But let's graph it anyway on a graphing calculator. I'm going to go zoom 6, and then I'm going to adjust things. Well, I guess we don't have to. So it has a y-intercept of 1. Can you, and by the way, what we're graphing right now is not the absolute value function, it's just the function itself. Can everybody find the x-intercepts of that function? You set y equal to 0. I want you to calculate or determine what the x-intercepts are of that function. You know, Colin?
Plus or minus root 5.
Excellent. Plus or minus root 5. We can calculate those numbers, but it doesn't matter. It's plus or minus root 5, which is approximately, for those of you that did calculate it, 2.2.
2.22.
Okay, so about 2.2. So there are x-intercepts here of this, and this is negative root 5, and this is positive root 5. So let me ask you a question. Without sketching this graph of x squared minus 5, where are the absolute value signs not needed? Well, they're not needed over here because the function will be above the x-axis. I hesitate in trying to draw something that's just going to look like a bad drawing. But this is going to go up and continue up. So as soon as you get past root 5, you don't need the absolute value signs. And similarly, as soon as you get past negative root 5 on the other side, you don't need them. That means that h of x will be equal to x squared minus 5 if x is greater than or equal to root 5, or if x is less than or equal to negative root 5. But if x is wedged between negative root 5 and positive root 5, then we have to multiply the argument of the absolute value function. In other words, we have to multiply x squared minus 5 by negative 1. Another way to look at this, so I'm going to draw x squared minus 5. I'm going to try it from a different angle. X squared minus 5 looks approximately like that. If this were yesterday and I said sketch the absolute value, then you would take every y coordinate down here and multiply by negative 1 to give us this. So everywhere between negative root 5 and root 5, you'd multiply the function by negative 1. That's what we've done. But this part, so I guess now I'm drawing the function of the original function, was already positive. So when x is greater than root 5 or equal to root 5, or less than or equal to negative root 5, we don't need the absolute value signs. And when I say we don't need them, I mean literally you just ignore them. You don't change anything. I think you get the drift here. The focus in this lesson is not for us to spend a lot of time graphing these functions. So let's do this last one just on our graphing calculator. Let's not even worry about the graph itself. Let's write the piecewise. And I want you to look up here just for a second. I hope that you have figured out that it's always going to be this, and it's always going to be this. You're always going to take and write the function without the absolute value sign, and then write it without the absolute value sign and multiply by negative 1. We're just going to use our graphing calculator to find out where those two things happen. By the way, looking at this function, you should know without the absolute value sign it opens down. So it's going to be the middle part that you leave alone. It's going to be the two endpoints that get reflected up. All we need to know is the x-intercepts, I guess. Negative x squared, nope, negative 0.5 x squared plus 2x plus 6. So notice we're doing this, we're not going absolute value. We're looking at the original function. Zoom 6. I'm pretty sure it crosses at negative 2 and positive 6. Can you confirm that? Okay? That means this central part is okay. By okay, I mean we don't even need the absolute value signs. And that includes, and I'm glad you asked that question earlier, Superman, that part that is okay includes the x-intercepts. So we're going to put for the domain of that great, there we go. We're going to put for the domain of that -2 is less than or equal to x, which is less than or equal to 6. And for the domain of these other parts, which is not okay, which need to be multiplied up by -1 to look like that, that would be where x is less than -2 or x is greater than +6. It's kind of the same thing we were doing yesterday, except now we're being more general. We're not just saying specific y values, we're saying a whole domain of y values that get multiplied. And that's tricky because I said a whole domain. You're looking at the x or the domain to determine when y gets multiplied by -1. And once again, this is a lesson or content that I think students get in the lesson, and then they start thinking about it later and they start to second guess themselves. That's kind of natural. You can see what the assignment is. Go ahead.
Should x be squared in the bottom of t still?
Yes, thank you for catching that, Sawyer. That should definitely be an x squared. In case you're watching this on video or you didn't catch what just happened there, I neglected to put a squared on that x, and it should have been x squared. All right. Incidentally, you know, this whole piecewise thing is not a huge deal moving forward to Math 30. Something that we'll encounter again in calculus. So page 377, I've got 9 to 14 there. I don't really believe you need to do every single question.